This is the first tutorial under the heading Calorimetry, and this is a chapter all to do with heat energy, temperature, and transfer of heat energy. And it's actually a continuation of a chapter you had in class 9. I don't know if you remember most of it, but just to begin with a few basics. Firstly, the difference between heat and temperature. Now, when you talk about heat energy of a body, say this is your object over here, and we're talking about its heat energy, we take into account two of its energies. The first is its kinetic energy, second is the potential energy. And here we're talking about the particles in the body, not the body itself. So the particles inside this body that make it up have a certain kinetic energy, and they'll have a certain potential energy. And when you add these two up, you'll get the total energy. Now this total energy is actually equal to the heat energy. And what is kinetic energy? Kinetic energy is the energy that's caused you to motion. You learn more about it in the chapters at the beginning of your book, which deal with motion later on, I think, in the year. But kinetic energy, just remember for now, it's caused due to motion of the particles inside, while potential energy is a sort of stored energy. It doesn't make anything move, but it's there, it's present, and it contributes to the total energy. Meanwhile, temperature, you see the definition written everywhere, is the average internal kinetic energy of the particles or molecules of the body. So in temperature, we're only taking into account the kinetic energy. So taking into account the motion of the particles inside. We're not taking into consideration the potential energy. So that's the main difference. Moving on, if you remember, if you've done the electricity chapters from the first chapter, you would have, if you remember the definition of potential, it's the electric state of a conductor which determines the direction of flow of current or electrons, whatever you want to say, when two bodies are kept in contact or there's a conductor joining these two. So what that means is that depending on the potential difference between the two bodies over here, say you have a wire joining them or they're kept in contact, you can say which direction will the electrons or the charge or the current be flowing in. Similarly for temperature, this is electrical energy. Now we're coming to heat energy. If we have two bodies again, they're kept in contact. If we know their temperatures, potentials, if we know their temperatures, then again we can determine the direction of flow of heat energy. So it's the same thing, except we're changing the electrical energy to heat energy. Now, the reason why we're saying heat energy all the time is because it is a form of energy. Just like electrical energy, light energy, sound energy, all the others, you'll be studying more about them later in the year again. But it's a form of energy, and every form of energy has a unit that's a common unit called joule. I'm pretty sure you know it already from the electricity chapters. So joule is the SI unit, symbol is J, but there's a unit which is much more unique and specific to this chapter, that's calorimetry, and that is calorie. So now you can see where the name comes from, and the symbol is Cal. So calorie is defined as the amount of heat energy that is required to raise the temperature of 1 gram of water from 14.5 degrees Celsius to 15.5 degrees Celsius. So say you have, I'm just going to draw this first. Remember these numbers, 14.5, 15.5. I'll tell you why we take them right now. So say this is 1 gram of water here. The amount of heat energy you need to change this temperature from 14.5 degrees Celsius to 15.5 is defined as 1 calorie. Now, why we take 14.5 and 15.5 and not just any temperature is because I'm pretty sure you've heard of this property of water before. It's called the anomalous. I'm not going to write the whole thing. Anomalous expansion of water. Expansion of water. So, what happens is that around the 4 degrees Celsius mark, there's a non uniform expansion of water. It basically shows very unique properties over here, very unexpected properties. So we don't need to bother much about that right now, but we should know that if we take 4 degrees Celsius to 5 degrees Celsius as our temperature change, water behaves in a very different way over here. So it's not going to give you correct results in this area, in this region. Only when you get beyond 14 degrees Celsius does it show a uniform and smooth expansion. So once you get past the 14 mark, so we're taking 14.5 just to give another 0.5, just to be safe, and then we take 15.5, and here we're assured that yeah, it will behave correctly and we'll get the correct results. So that's why we take 14.5 and 15.5 and not just anything. Now, 1 calorie, the relation between 1 calorie and 1 joule is that 1 cal is equal to 4.186 joules. So we can round it off to 4.2, and that's what you'll be using throughout the chapter. Now, similarly, we can have a kilocalorie, and that'll be the heat energy required to not raise the temperature of 1 gram of water from 14.5 to 15.5, but raise the temperature of 1 kg of water from 14.5 to 15.5. And you can then directly also say that just multiply this number over here by 1000, so 1 kilocal, that's kcal, is equal to around 4200 joules. Now, there's a formula which is a basic formula in this chapter. I should erase this first before I tell you that. Okay. I think you guys would have done this before, and I think last year you may have done it, I don't remember. But it was something like this. Q is equal to m.c. delta T. Q is the heat energy. M is a mass. I'll explain this. I'm just telling you what they stand for first. So M is mass. C is a specific heat capacity. And delta T. Delta always denotes a small change. So delta T means change in T. So what this formula tells you is that, say you have an object, it's made of a certain material, and by the way, every material has a certain value, a specific heat capacity. We'll come to that in a minute. But say your mass is m and it has certain specific heat capacity, and you want to bring about a change of temperature, say from 20 degrees, it's at 20 Celsius originally, you want to bring it all the way to 40 degrees Celsius, and you want to find out how much heat should I give it, how much energy should I provide in the form of heat. So all you need to do is apply this formula. Delta T is change in temperature, so just minus the two temperatures, 40 minus 20, so your delta T will be 20, not 40, not 20 from here, but 40 minus 20, so 20 from this subtraction. Multiply 20 by the mass and the specific heat capacity, and you'll get a value. That's the heat you need to carry out this change over here. And I'm out of time in this tutorial, so I'll be carrying on from here in the next one. But for now, just remember this formula. We're going to be discussing it further in the next video.